You're probably used to functions being, a curve on a flat piece of paper. But what if we could use a function to describe an entire mountain range, or maybe the air pressure in a massive weather system? Well, that's exactly what we're going to do today. We're adding a whole new dimension, moving from simple lines to incredible 3D surfaces.
All right, so to get a handle on these incredible mathematical landscapes, we've got to start with a really powerful shift in how we think about functions. Okay, so on the left, you've got the world you know and love, right? Single variable calculus. You put in one number, x, you get out one number, y, and you plot a nice 2D curve. But on the right, that's where the magic happens. Our function z equals f of xy takes in a pair of numbers, an x and a y coordinate, and spits back a single output, z, which we can think of as the height. That tiny change is everything. It's the difference between drawing a line and sculpting a mountain. And this brings up a huge question. Our world is 3D. Our screens are flat. So how in the world are we supposed to draw, let alone even wrap our heads around, these complex surfaces? Well, luckily mathematicians have come up with some pretty clever tools to help us out.
The first tool is actually super simple, but really elegant. It's like, if you can't figure out a whole puzzle, you start with one piece, right? We're going to learn how to understand these surfaces by taking slices, and we call these slices traces.
So what exactly is a trace? I want you to imagine you have a 3D surface and you slice right through it with a perfectly flat vertical sheet of glass. The curve that gets etched onto that glass where it intersects the surface, that is a trace. It's a way of getting a simple 2D cross-section of a really complex 3D shape.
And here you can see exactly what I'm talking about. See, what we're doing is we're locking one variable in place. Let's say we just fix y at some constant value, b. Bam! That creates this vertical wall that slices right through our shape. The curve we see on that wall is the trace. We've just turned a tough 3D problem into a much simpler 2D one, just figuring out the shape of that one curve.
And the cool thing is, we don't have to stop there. We can take another slice where x is constant, and that shows us a different curve. Then we do it again where y is constant. It's kind of like you're building a digital wireframe of the object, piece by piece. By looking at all these different cross-sections from multiple directions, our brain can start to stitch them together and build a mental picture of the entire 3D object.
Okay, so slicing vertically gives us these cool side views. But what if we want the bird's eye view, the view from the top down? Well, for that, we're going to borrow a trick from map makers, something they've been using for centuries: contour maps. This image just nails the concept. Up top, you've got the real 3D landscape, and down below, that's its 2D contour map. Every single line on that flat map connects points that are at the exact same elevation. Where the lines are all bunched up, the mountain is super steep. Where they're spread out, it's a nice, gentle slope.
Now, in math, we have a fancy name for these lines. We call them level curves. I want you to think of it like this. Instead of slicing with a vertical wall, we're now slicing with a perfectly horizontal plane, like a sheet of glass floating at a certain height, which we'll call k. Every single point on the curve we get has the same z value. Then we just take all those horizontal slices and project them down, kind of smush them onto the floor. That's our contour map.
And this idea is just so powerful because it pops up everywhere. If our function is measuring height, then yeah, the level curves are the contours on a map. But if our function is measuring air pressure, those same level curves are the isobars you see on the nightly weather forecast. It's just a fantastic tool for visualizing all kinds of 3D data in 2 dimensions.
Okay, enough theory. Let's get our hands dirty and actually put these tools to the test. Let's see if we can build a shape we all know and love, starting with nothing but its formula.
All right, here's our first patient. I know, that looks a little scary, but believe it or not, that formula describes the top half of a perfect sphere with a radius of 3. Our mission is to see if we can discover that shape just by analyzing its level curves. So, how do we start? Same as before. We set our function equal to a constant height, we'll call it k. And when we do the algebra for different heights, like you see in the table, look at this, a beautiful pattern starts to show up. Down at the base, where the height is 0, we get a big circle with a radius of 3. As we raise the height, the circles get smaller and smaller, until we get all the way to the very top where it's just a single point.
So on the left, that's our 2D contour map, the result of all that math we just did. A bunch of circles inside circles. But now for the magic trick. Imagine we take each one of those circles and we lift it up to its proper height, okay? What happens? They stack up perfectly, and bam, there's our hemisphere on the right.
We just completely reconstructed a 3D object using only its 2D contour map. So cool.
All right, that was pretty cool, but we kind of knew what we were looking for, right? A hemisphere. The real test of these tools is when we're faced with a function that's totally mysterious. So let's try something a little weirder.
Okay, so what in the world does this thing look like? I mean, looking at that formula, I have no idea. There's no obvious shape that comes to mind. So let's bring out our level curve strategy and see what secrets it can tell us.
Okay, let's start with what we know. Step 1, set the function equal to our constant k. But here's where we get clever. Instead of just picking random points, let's see what happens if we travel along a straight line that goes right through the center, the origin. That's aligned with the equation y equals mx. When we plug in mx for y everywhere, and watch this, the algebra it collapses in this amazing way. All the x's just cancel out, and we're left with a value that only depends on m, the slope of our line.
Okay, pause. You have to think about what this means. It means that for any straight line you draw out from the center, the height of our surface is the same all along that line. So our level curves, they aren't even curves. They're just straight lines shooting out from the origin. How wild is that? We never would have guessed that just by staring at the formula.
All right, let's take a step back and just recap what we've uncovered here. We've basically learned a new way to see, a way to translate these abstract, complicated formulas into actual, tangible 3D shapes.
So what's the big takeaway here? First, functions with two inputs, x and y, aren't just lines. They describe entire 3D surfaces. And we have two main tools to understand them. We've got traces, our vertical slices, which give us a cross-section, and then there are level curves, our horizontal slices, that give us that awesome bird's-eye view, the contour map. Together, these things let us decode and actually see what these complex shapes look like.
And that kind of leaves us with one last thought. Think about it. We just took a really complex, abstract object and made sense of it by slicing it up and looking at it from different angles. And it just makes you wonder, right? What other big, complicated problems, maybe in science or art or even just in our own lives, could suddenly become clear if only we learned how to look at them from a new perspective?